Welcome to asymptotic notation. Why we need asymptotic notation? We all write algorithm, but the algorithm should be efficient. The efficiency is the algorithm should be time efficient as well as space efficient. Time efficient is the number of counts, number of times the basic operation of an algorithm executed. And space efficiency is the count, the memory space consumed by the algorithm. We have order of growth. Order of growth is for measuring the time efficiency. In order of growth, we have n square, n cube, log n log n, and etc. To compare and rank such order of growths, we use asymptotic notation. We have 5 notation. Now we are going to see about big O. Let's start with big O. We consider two functions, f of n and g of n. They are positive functions. F of n is for algorithms running time, and g of n is a function to compare the count. We say f of n belongs to big O of g of n only if f of n is lower bound of a constant multiple of g of n. For all, n should be large. Mathematically, we represent this as f of n is lesser than or equal to g of c of g of n, c into g of n. C is a constant. With graph, we represent this as f of n is lower bound of g of n. This is f of n and some constant multiple of g of n. And this is the don't care part. We don't consider this. let's see an example. It's 4n square plus 2n plus 1 belongs to big O of n cube. Compare this with f of n belongs to big O of g of n. So f of n is 4n square plus 2n plus 1 and g of n is n cube. We know that f of n is less than or equal to c into g of n. So first let's apply n is equal to 0. We will get 1 less than or equal to 0 and this is false. Then let's apply n is equal to 1. When we apply n is equal to 1, we will get 7 less than or equal to c. Let's assume that c is equal to 7. With c is equal to 7, we apply n is equal to 2. We will get 21 less than or equal to 56. This condition is true. And let's apply n is equal to 3. We will get 43 less than or equal to 189. For this, let's plot a graph. This is n naught. When we plot the graph, we will get something like this. And this is f of n and this is g of n. So f of n is lower bound of g of n. There is a shortcut for this. For this, we should compare the degree of f of n, g of n. Let's see one example. It's n square plus n plus 1 belongs to big O of n cube. Compare the order. This is f of n. F of n's order is degree is 2 and g of n's degree is 3. Obviously 2 is less than or equal to 3. So the given is true. And this is another example. Compare the degree of f of n and g of n. We will get degree of f of n is 3 and degree of f of g of n is 2. This condition is false. So the given equation is false. This is the shortcut for finding whether the f of n belongs to big O of g of n. Thank you.
Now we are going to see about big omega notations. It can also be called as higher bound or tight bound notations. Here we can consider two functions f of n and g of n. F of n is said to be in big omega of g of n. F of n is a positive constant multiple of g of n. We can express it as f of n belongs to big omega of g of n. Thus f of n is greater than or equal to big omega of g of n. Thus c is a positive constant and n naught is greater than or equal to n is greater than or equal to n naught, where n naught is non-negative integer. The graph can be given by here f of n is higher bound of g of n and this is the doesn't matter region. Let us see an example. And q plus n square greater than or equal to big omega of g of n. Thus f of n is greater than or equal to c into g of n. Here we can put n is equal to 0. The 0 plus 0 greater than or equal to c into 0. Thus this condition is false. When n is equal to 1, 1 cube plus 1 square greater than or equal to c into 1. Thus 2 greater than or equal to c into 1. So assume c is equal to 2. When n is equal to 2, 2 cube plus 2 square greater than or equal to c into 2. Plus 8 plus 4 greater than or equal to 2 into c. 12 greater than or equal to 2 into 2 plus greater than or equal to 4. 12 greater than or equal to 4. When n is equal to 3, n cube plus n square greater than or equal to c into 3. 27 plus 9 greater than or equal to c into 3. 36 greater than or equal to 3 into 2, 6. Therefore the condition is true. Let us draw the graph for this 0, 0 and 0, the graph will be f of n and g of n. Thus the f of n is higher bound of g of n, and this is doesn't matter region.
Now let us see about big theta notations. For big theta notations, we have two equations. Let's consider f of n and g of n. The notation is represented as f of n should be greater than or equal to a constant multiple of g of n, or it can be greater than or equal to the same equation. That means in the mathematically we represent it as f of n belongs to big theta of g of n. This means that the equation f of n is both upper bound by g of n as well as lower bound by g of n. This is a don't care region. Let us see an example. Consider the equation 4n square plus 16n plus 2 belongs to big theta of n square. Mathematically, when we represent it as, we get it c1 into n square should be lesser than or equal to 4n square plus 16n plus 2 greater than or equal to less than or equal to c2 of n square. Now let us consider this region. So we'll get 4n square plus 16n plus 2 less than or equal to c2 of n square. When we apply n is equal to 0, we get 2 less than or equal to 0. This condition is false. When applying n is equal to 1, we get 4 plus 16 plus 2 less than or equal to c2, which is 22 less than or equal to c2. Now let us assume c2 to be equal to 22. When applying for n equal to 2, we get 16 plus 32 plus 2 plus c2 into 4. So that applies as 50 less than or equal to 88. The condition is satisfied. Similarly, when applying for n equal to 3, we get 36 plus 48 plus 2 less than or equal to c2 of 9, which results in 86 less than or equal to 198. Therefore, the condition is true. Now we can finally assume that c2 is equal to 22. Now consider the other side, the left hand side. We get C1 into n square less than or equal to 4n square plus 16n plus 2. Normally, when you consider the equation, you're supposed to find C1, but there's a shortcut to do this. The shortcut would be consider the highest coefficient of f of n. Now that will become 4. So we're going to assume C1 equal to 4. When you apply in C1 equal to 4 and now n equal to 2, we get C1 into 4 less than or equal to 16 plus 32 plus 2, which results in 16 less than or equal to 50. The condition is true. Now when applying in n equal to 3, we get C1 into 9 less than or equal to 36 plus 48 plus 2, which results in 36 less than or equal to 198. Therefore, the condition is true. When we draw the graph for these equations, we get this has to be f of n. This is a higher bound, that is C2 into g of n, and this is a lower bound, C1 into g of n, and we get the don't care region. That's it for big theta.
Now let's see about small o and small omega. First is small o. F of n is equal to small o of g of n if and only if limit n tends to infinity, f of n by g of n is equal to 0. The ratio between f of n and g of n must be 0. It shows that g of n is variably bigger. Now let's see about small o and small omega notations. First is small o notation. In this, f of n equal to small o of g of n if and only if limit n tends to infinity, f of n by g of n is equal to 0. The main idea is the ratio between f of n and g of n must be 0. It means g of n is variably bigger than f of n. Variably bigger means if you cancel both f of n and g of n, some part of g of n will remain, which leads to 0. Now
Let's see an example. f of n equal to n and g of n equal to n square. Now limit n tends to infinity, f of n by g of n is equal to n by n square. If you cancel, we will get 1 by n. By substituting the limit 1 by infinity, which is equal to 0, such that we proved f of n belongs to small o of g of n, and the graph will be represented as f of n plus g of n, like this. F of n. This shows that g of n is strictly higher bound of f of n. Now we can see about small omega notation. In this, f of n is equal to small omega of g of n if and only if limit n tends to infinity, f of n by g of n is equal to infinity. To prove this, let us take an example. F of n is equal to 3n and g of n is equal to 2n. Then applying the formula, limit n tends to infinity, f of n by g of n is equal to 3n by 2n. Since the power is same, we can write this as 3 by 2 the whole power n, which is equal to 1.5 whole power n. When you apply the limit, it becomes 1.5 whole power infinity, which is equal to infinity. Thus, we proved f of n belongs to small omega of g of n, and the graph is represented as f of n plus g of n, like this. F of n and g of n. In this, f of n is strictly higher bound of g of n.